Welcome everyone to this FLOW seminar, and FLOW stands for Federated Learning One World seminar. So today we have Jongho Park speaking. He has been at KAUST for a very long time, and now in February moved to KAUST, which is very close in edit distance somehow, but at a different location. And he said he's a bit outsider to the field of federated learning. He worked a lot on subspace correction methods, which he will explain to us in a few minutes. And he found an application to federated learning. And okay, so the floor is yours. We're happy to listen to your talk.
Okay, so yeah, thank you for the very nice introduction. And as Sebastian said, frankly speaking, I think I'm not an expert in the field of federated learning, but if someone asks me, what is your research interest, then I reply as my research interest is numerical analysis. So to solve partial differential equations or linear systems or nonlinear equations, something like else. But because I had a chance to get an opportunity. I had a chance to know the field of federated learning, and recently I made some research, which is far from perfect, but it is my great honor to share my research on federated learning in front of these experts on federated learning. So today I'm going. My subject is dual FL or duality-based federated learning algorithm with communication acceleration in the general convex regime. And this is the contents for my presentation. As a first, I'm going to introduce how a stranger like me met federated learning. And actually, my original research interest is called subspace question. So I just briefly introduced the notion of subspace question. And I want to introduce the duality between federated learning and subspace question. So just want to share that how subspace question theory helps design of the efficient federated learning algorithm. And the result is called dual FL, which stands for dualized federated learning algorithm. And I want to explain the convergence theory very briefly, and then conclude my talk. And this slides and my talk is based on my recent paper, co-worked with my current principal investigator, Professor Jin-Chao Xu, and this paper can be found in arXiv. Okay. Actually, as I said just before, my primary research interest is called subspace question method, or in other words, domain decomposition method. And domain decomposition method is a kind of numerical scheme that splits a given partial differential equation into coupled problems on smaller domains, which forms a partition of the original domain. And actually, this figure is a symbol of domain decomposition method. And I will explain the reason that why this figure is a symbol for domain decomposition method. And actually, this domain decomposition method is a very active research area particularly in numerical analysis and scientific computing for several recent decades, especially for massively parallel computing and simulation and analytics related to partial differential equations. And I want to mention that the 28th International Conference on Domain Decomposition Method will be held on KAUST, my current affiliation, on the next year. And actually, the starting point of this domain decomposition method is 1870. And the Hermann Schwarz developed a method called Schwarz alternating method. And actually, this was not a computer algorithm because at 1870, there was no computer. So this is not a computing algorithm, but he suggested this method to prove that the solution of this Poisson equation on this ugly domain exists and unique. So actually, he proved the existence and uniqueness of solution of this partial differential equation in a way that the solution U can be formed as a limit of a sequence where the sequence UN can be formed by we first solve the small problem on this circular disk, and then using the solution of the circular disk as a boundary value of this rectangular domain, we solve on the rectangular domain, and then we solve on the circular domain alternately, and we finally this sequence converges to the unique solution of this partial differential equation on an ugly domain. And this is the starting point of domain decomposition method. And in recent years, this domain decomposition method serves as not only some theoretical tool, but also some computational algorithm. Because this domain decomposition method, they can be designed to be suitable for distributed memory computers in a way that each node corresponds to a single subdomain problem, so that in a distributed memory computer, the node 1 corresponds to the subdomain 1, and node 2 corresponds to subdomain 2, and so on. And a very large problem can be split into a number of small problems, and each of them can be solved in parallel, so that it is very efficient on parallel computers. And here, the most important aspect is the communication cost. That is, in designing domain decomposition method, communication cost dominates. And this characteristic is shared by federated learning. So in domain decomposition method, our main goal was to design scalable algorithms in a way that if we have a very large problem, then we can solve this large problem very fastly. If we have a large number of computers, then we can split this large problem into a number of small problems, and then we solve it in parallel. And actually, as I said, this kind of domain decomposition method seems very far from federated learning. It is totally different. But I met federated learning in the last year. Actually, in the last year, I was visiting Jinchao at Penn State to study this domain decomposition method further, because Jinchao is a world-renowned expert in this domain decomposition method. And there was an invited talk of Peter about PROC-skip, which is the very well-known algorithm in federated learning. And after I participated in this invited talk, Jinchao said to me that, what do you think about this algorithm? So I just replied that, I can make a similar algorithm to PROC-skip. Then he said that, then please join my group in KAUST. So I just moved my affiliation to KAUST. So this federated learning became a motivation to move my affiliation, and so now I'm in KAUST and studying with this new subject. So I think that almost of the audience here knows much better than me about federated learning. So it is a bit shameful to introduce federated learning in front of you. But just for completeness of this presentation, I just included several slides on federated learning. So in federated learning, each client has its own data set, and they update local questions separately, and update global model maintained by an orchestrating server via local data set or local training algorithm only. And the main issue is the communication cost. So the federated learning algorithm should be designed toward the direction that the amount of communication among the clients is reduced. And usually, this kind of federated learning problem is modeled as consensus optimization. That is, we want to minimize the cost function, which consists of the sum of n local cost functions fi. So here, omega stands for the parameter space, and large N stands for the number of clients. And here, each fi is a local cost functional, depending on the local data set and local client. And based on the Peter's recent paper on the accelerated federated learning algorithms, this kind of federated learning algorithms can be classified into 5 generations. In the first stage, which is called heuristic age, there are several algorithms to there are several algorithms to tackle the federated learning by using some kind of local training. That is, each client train its own data set separately and then just communicate very seldom. But although these algorithms perform very well, but there were no convergence theory. And in the next age, the called homogeneous age, some convergence theories were developed under some similarity conditions. For example, all the local data sets are assumed to have some bounded gradients or bounded gradient diversity. And next, the next age is called sublinear age, and in this age, some of algorithms are shown to be converged sublinearly. But this is far from the practice, because in practice, federated learning algorithms usually converges faster than sublinear convergence. And recently, in some works, it was shown that several federated learning algorithms converge linearly, where the convergence rate depends on the condition number kappa of the problem. And the most recent age, called the accelerated age, and it started with the pioneering work of Proxkip, and from this age, the algorithms are shown to be linearly convergent. And here, the convergence rate depending on not kappa but on square root of kappa. And this kind of convergence rate is known to be optimal in the sense of communication on distributed learning, distributed complex optimization. And this SCAP-new, or also known as Proxkip, this is the first federated learning algorithm with local training that achieves the optimal communication complexity. And I was motivated with this result. And actually, this is a combination of three different items. The first one is that it is a forward-backward splitting algorithm applied for this alternating formulation of consensus optimization. That is, we assume that each client has a separate variable zeta I, but they are forced to be satisfy this equality constraint. And in order to circumvent the problem of client drift, the suitable gradient shift scheme should be applied to ensure fast and robust convergence of the algorithm. And the main idea of this SCAP-new is that we communicate with only small probability. I mean, so it is equivalent to say that in forward-backward splitting algorithm, we do not perform backward step at every iteration, but we perform backward step with a small probability only. And I just copy and paste. I just copy and paste this algorithm from this SCAP-new paper, and here we perform this forward gradient step, and we communicate over clients with probability P only, and then we update this gradient shift term. So this is the three main parts of SCAP-new algorithm, and these achieve the optimal communication rates in federated learning algorithm. So in this talk, motivated by the SCAP-new algorithm, I want to explain the notion of duality between federated learning and subspace question. Actually, this kind of duality is not new, and it is well known in the field of complex optimization. But just I want to explain this to emphasize its usefulness on federated learning. And then, based on this duality, I want to introduce my new algorithm called dual-FL. And this algorithm achieves communication acceleration in the general convex regime. That is, we don't need we don't need assumption like smoothness or strong complexity of the host function to ensure this communication acceleration, but we only need complexity of fusion. Next, I already spent 10 minutes, so I have to go faster. But I want to just briefly introduce the notion of subspace question very fastly. So as I said before, this notion of subspace question method originates from the field of numerical analysis. So in numerical analysis, we want to solve the linear system or nonlinear system. So suppose that we want to solve a linear system AU equals to F. Here A is a matrix and U and F are a vector. And here, subspace question method is described as follows, that we assume that our solution space V is decomposed into the sum of subspaces Vk. Here, this Rk star is called prolongation operator, or it is an embedding. That is, we can simply assume that Vk is a subspace of V. Then we compute local corrections in subspaces independently. That is, in each subspace Vk, we solve the local problem defined in terms of AK, which approximates this local the restriction of the global operator A well, and we solve this local problem, and then we obtain this local correction WK. Then we iterate our guess by some suitable combination of local updates WKs. That is UN plus 1 is written as the sum of UN and some combinations of WK. And this method is called subspace question method. Actually, this framework is very general and very abstract, but it is known that almost of the existing modern numerical methods for linear systems can be represented in the framework of subspace question method, starting from the Jacobi or Gauss-Seidel method, which appear in the textbook of numerical analysis, to multigrid or domain decomposition method, which can be found in very recent research papers on numerical analysis. For example, if we suppose that our solution space is R to the n, and we assume that each subspace is the subspace Vk is the space for the k's coordinate, and if we apply successive subsequation, that is, we update U in a cyclic manner from V1, V2 to Vk, then it is just Gauss-Seidel method. And if we update all the subspaces Vk simultaneously, then it becomes Jacobi method. In this way, the subspace question method can explain almost of the existing numerical algorithms for linear systems. And actually, as I mentioned before, for local solvers, we don't need to solve the problem exactly, and we can adopt inexact local solver, and it corresponds to some kind of SOR iterations, which is well known in numerical analysis. And as another example, if we consider some partial differential equations defined on some domain omega, and if we define the subspace Vk as some function space defined on the subdomain omega k, then it becomes the domain decomposition method, especially called Schwarz method. So if we apply successive subspace question method to these partial differential equations, then it is called multiplicative Schwarz method. And on the other hand, if you apply parallel subspace question, then it is called additive Schwarz method. And actually, this is my primary research interest. And this kind of subspace question method can be easily extended to convex optimization. Here, we use the same space decomposition setting, and we solve some kind of local optimization problem which approximates this local energy functional. Then we update our solution sequence UN by some combination of local updates WK. And this kind of subspace question methods for convex optimization have been developed very actively in recent decades, and this slide just summarizes some recent development of subspace question methods for convex optimization. So I'm just gonna skip them. And this framework has many applications in mathematical imaging, nonlinear partial differential equation, and optimal control. So I just want to mention that it has very broad range of applications in numerical analysis. And now I move to our original topic, federated learning, and I want to explain how I designed the federated learning algorithm based on this subspace question theory. So we revisit this mathematical model for federated learning here. We want to minimize the average of n local cost function and fi. Actually, in this problem, we have to deal with this fi separately. And this is true for operator splitting, because we wanna deal with F1, F2, and so on, Fn separately, but they share the common variable zeta. But on the other hand, subspace question method, this is a kind of variable splitting, and it seems not suitable for federated learning because all of the local cost functions share the same variable and it cannot be split into the clients. However, uh, However, it is possible to consider not this original formulation, but some kind of dual formulation of this problem, which is more suitable for applying parallel subspace correction than this original formulation. Actually, this kind of idea that considers dual formulation instead of the original formulation was considered in this 2015 paper to solve some mathematical imaging problem. But in my talk, I want to apply this idea to solve federated learning problem. And actually, I believe that almost of the audience here are already familiar with this kind of duality theorem called Fencher-Rockefeller duality. So if we consider this kind of minimization problem, which minimizes the sum of two functions f and g, then this problem can be dualized into this equivalent dual problem, which is defined in terms of convex conjugate f star and g star, and the solutions of this primal problem and solutions of this dual problem, they are related by this primordial relation. Hence, in order to obtain a solution of this primal problem, it is enough to solve this dual problem instead of the primal problem, and then use this relation to recover a primal solution. And before starting to construct a specific dual formulation of federated learning problem, I want to assume that we have a strong convexity solution. That is, each of the local cost function fj is strongly convex with parameter mu. In this case, we can redistribute strong convexity term of the local cost function fi to make our problem like this. That is, each gj is fj minus this one, and we just reallocate this strong convexity term like this. And then we apply this Fencher-Rockefeller duality, then we obtain this kind of alternative formulation. Actually, this formulation, I found that this formulation already appeared in some existing papers, but when I first designed this paper, I was not aware of the existing works. So we consider this kind of dual formulation, and this dual problem has a property that this dual cost functional is strongly convex, and the primal solution zeta star can be recovered from the dual solution psi star by this relation. And hence, if we obtain the solution of dual problem, then we can recover the primal solution zeta by using very simple algebraic arithmetics. And as you see, this dual problem has variable psi1, psi2, and so on, psi n, and then each psi j is split into this gj star. So this dual problem is finally suitable for parallel subspace correction. And if we naively apply this parallel subspace correction method to this dual problem, that is, at each iteration of this algorithm, we optimize the local problem only, and then we combine this local solution to obtain the global solution. Then we obtain this algorithm, and we can simply obtain a linearly convergent federated learning algorithm, which converges with the rate 1 minus 1 over kappa. But unfortunately, we are living on the 5th stage of federated learning, and if we are living on the 4th stage, then this is good. But because we are living on the 5th stage, which requires an algorithm that is linearly convergent with the rate depending on square root of kappa, this is not enough. So hence, we need to further develop this algorithm to achieve faster convergence rate. Students, and to accelerate this parallel subspace correction method, we wanna first observe that this dual problem can be represented as a composite optimization problem. Here, this dual energy function, dual cost function ED can be represented as a sum of FD and GD, where FD is defined like this, which is smooth, and GD, is defined as this one. This one is not smooth in general, but it is strongly convex. And for this kind of problems, it is known that for the backward splitting algorithms, which deals with the smooth term and non-smooth term separately, are well suited for solving this problem. And actually, in one of my previous work, I showed that parallel subspace correction method is indeed a fourth backward splitting algorithm. More precisely, this parallel subspace correction method can be written in terms of inexact fourth backward splitting algorithm like this. That is, we have smooth term, and we have smooth term, and we have gradient descent with step size 1/n, but we have some kind of inexact non-smooth term. So the idea is that we simply replace this fourth backward splitting algorithm with accelerated algorithm. And there is a very well-known accelerated forward backward splitting algorithm called FISTA. So we just simply replace this iteration by a FISTA iteration. Then we obtain this algorithm. That is, this algorithm is not a new, but this is a FISTA applied to a particular dual formulation or federated learning problem. Then we can obtain this kind of accelerated convergence. But this algorithm is not enough, because this algorithm does not show any property of federated learning. This algorithm does not show the aspect of local training or some kind of distributed computing, but this algorithm shows only a structure of FISTA. So in order to make a federated learning algorithm, we have to consider a procedure called pre-dualization. Actually, this is the algorithm called dual-FL, my proposed algorithm, and this algorithm can be constructed by applying pre-dualization to FISTA. Let me first briefly explain my dual-FL algorithm. First, we solve this kind of local problem, which is defined by combination of local cost function and some gradient shift by local training algorithm. And then we apply communication among the clients, and then we apply acceleration by over relaxation defined in terms of a FISTA momentum. And actually, this dual FL, which seems far different from the original FISTA algorithm, but we can prove that these two algorithms are actually equivalent in terms of pre-dualization. This pre-dualization is a notion that was proposed in 2017 and 2020, and this pre-dualization is a procedure that makes an algorithm to solve dual problem, and a procedure that converts an algorithm to solve dual problem to an equivalent algorithm to solve the primal problem. Actually, we can show that in dual FL algorithm, we had the sequence Xi and eta, and we can recover. We can show that the sequences generated by dual FL and sequences generated by FISTA, they are related by the simple algebraic formulas. That is, it means that these two algorithms are actually equivalent. So using this relation, let me summarize how to construct this dual FL algorithm. We first have this federated learning problem, and then we dualize this problem to obtain this dual formulation, and then we apply parallel subspace correction method, and then we apply acceleration, then we obtain some FISTA for solving this dual formulation, and this achieves optimal convergence rate, and then we pre-dualize this algorithm to obtain our final algorithm called dual FL. And I wanna highlight that this dual FL is applicable even when the cost function, the original cost function E, is non-smooth, because we are playing with dual formulation. Even though it is possible that even though the original primal loss function is non-smooth, it is possible that dual dual cost function is smooth. So this dual FL is applicable even when the cost function is non-smooth. And as I mentioned before, we assumed that the cost function is strongly convex. But even if the cost function is not strongly convex, we may adopt some kind of regularization technique to deal with the non-strongly convex objectives. And this communication acceleration of this dual FL is guaranteed in a deterministic manner. Actually, when I first considered this dual FL algorithm, I thought that my algorithm is the first algorithm to guarantee the acceleration of federated learning algorithm in deterministic manner. But recently, I found the existing works, which was published in 2022, which guarantees the acceleration of federated learning algorithm in deterministic manner. So my dual FL algorithm shares the advantage with this result. And because and I want to also highlight that any training algorithm can be adopted as a local solver. Now we move to the convergence theory. Actually, there is nothing new in my convergence theory because there are a bunch of literature on the convergence theory of Vista, and just I want to simply adopt them. So, in dual FL, because in practice we are not able to solve local problems exactly, but we have to solve local problems inexactly. I mean, we have to solve local problems up to a certain level of accuracy, and then we stop. So, in order to describe the criterion for inexact local solvers, I wanna present some basic facts on the duality of local problem. It means that if we consider the local problem of this dual FL, then it is equivalent to this dual problem. And if we if we consider the solution, the primal solution theta j and the dual solution psi j, then they satisfy that this primal dual gap vanishes. Therefore, we can consider the primal dual gap, which is defined like this, as a stopping criterion for the local problems in dual FL. Now we assume that we first assume that each Fi is mu strongly convex, and we assume that each local problem in my dual FL algorithm is solved up to the accuracy this one. Then we can ensure that the convergence rate of this dual FL is proportional to 1 over n squared, which is optimal. And as far as I know, this dual FL is the first federated learning algorithm that achieves communication acceleration even when the cost function is non-smooth. And now we further assume that each Fi is mu strongly convex and L smooth. In this case, if we suppose that each local problem is solved up to this level of accuracy, then we can achieve the linear convergence rate, where the linear convergence rate is given by 1 minus square root of rho. Here, this rho is proportional to the condition number of the problem. So that we can say that this dual FL achieves the optimal, this big O of square root kappa communication complexity of distributed complex optimization. And next we drop the assumption that each Fi is strongly convex. So we assume that sorry. No. Next we wanna discuss the the complexity of local problems. And because we can adopt any local solvers, or we can assume that each local problem is solved by an optimal first order complex optimization algorithm. And in this case, if we assume that each Fi is mu strongly convex and L smooth, then we can prove that the local iteration complexity satisfies big O of square root of kappa. And this rate agrees with many of the existing results, such as scat nu. And as I mentioned before, my algorithm can be applied for the case when the cost function is not strongly convex, by using this kind of introducing this kind of regularization term. Then even in the situation that the cost function is only merely convex, we can ensure that our dual FL algorithm converges to a solution. And if we assume that each Fi is smooth but not strongly convex, then we can assume that the communication complexity, the number of communication round, is bounded by big O of 1 over square root epsilon. And this rate agrees with the optimal estimate for first order method to minimize gradient norm, which was presented in this paper. Now I want to summarize a table that I want to present a table that summarizes a comparison between my dual FL algorithm with other 5th generation federated learning algorithms. Here, I believe that this table is not complete because there are also many recent algorithms developed for accelerated federated learning. But anyway, I compare my algorithm with this SCAPNU and APDA and 5GCS and RANDPROX. And differently from all the existing algorithms, this dual FL can be applied to non-smooth and convex regime and smooth and non-strongly convex regime. And similarly to this APDA and 5GCS, this kind of the acceleration of communication can be ensured in a deterministic manner. Okay, and I spent 40 minutes, and it is time to conclude my talk. So to wrap up, I just explained how federated learning and the subspace question method are related. Actually, this federated learning is a topic in machine learning, and the subspace question method is a topic in numerical analysis. So they seem to be very far from each other, but they are actually closely related. And then, based on the relation between federated learning and subspace question, I proposed a new federated learning algorithm called dual-FL, and this algorithm achieved communication acceleration in the under very general assumptions. And actually, I'm considering several topics for future works. And actually, recently, I submitted my paper to some conference, and it was rejected. And the main criticism is that the range of application is too slim. It means that because my work is based on the convexity assumptions, and this assumption is too strong. So I'm trying to extend my result to non-convex setting, but I think that this topic is quite challenging. And I also have to consider several other important aspects of federated learning, such as client sampling and communication compression. Actually, these kind of aspects are already dealt in some existing works like this. And I'm trying to equip this client sampling and communication compression to my algorithm, and this is a currently working project. And finally, because there is some kind of discrepancy between two-field subspace question method and federated learning, I want to transfer some knowledges from subspace question method to federated learning and vice versa. And it will result in many valuable fruits. And because I'm a stranger in this federated learning field, I want to get some idea from the audience on what should I do, or what can I do for to improve my work. Okay, thank you for your attention.
Okay, thank you very much. Let's I don't know, clap virtually or raise our hands. Okay, thank you very much. I really liked the introduction. No, it was a bit, yeah, exactly. We don't see this usually in these flow seminar talks. Now you bring some insights from a different field to then design a similar algorithm that somehow works out of the box. But then just to clarify, to get this this acceleration, you had basically to apply real acceleration techniques inside your framework, to get this square root of kappa. So, and if I understood correctly, there was this other paper you mentioned in the footnote. They basically apply directly acceleration to the first problem, or how does it work? Or the question is maybe a bit more open. I mean, what would happen if you just run accelerated method on the primal problem? What would be the difference to your method?
Actually, because this kind of, let me see. This kind of algorithm like SCAPNU can be regarded as an acceleration algorithm that is applied directly to the primal problem. But
Okay.
According to the paper of SCAPNU, it is challenging to design accelerated algorithm with local training because actually the accelerated algorithm without local training is easy to design. We can simply apply Nernst momentum, then that's all. But if we execute Nernst accelerated gradient method and skip some communication, then it will diverge. So it is very it was very challenging issue to design accelerated algorithm under the assumption of local training. And this SCAPNU was the first result as I know. So, but when I first knew about this result, just I wanted to use the idea of accelerating dual problem instead of this primal problem. So this was my motivation.
Okay, thanks. That clarifies a lot. So are there questions from the audience? So you can raise your hand and I can unmute you to ask directly or give other comments or. Well, okay, so maybe I can ask there are many experts in the audience, so I'm sure they all have questions. Yeah, so did you, I mean, currently now that there seems to be a long list of algorithms now that all have similar rates, as you also showed in this table.
Yes.
Did you compare them sort of numerically, or do you have some intuition which might work better than others, or you expect all to be more or less the same?
Yes,
because
actually,
the rates is the same.
Actually, after my last slide, there are some numerical results, but I did not show you because because I want to be humble and because I want to be humble, and if I say that my algorithm is better than the existing federated learning algorithm, then it may be a false statement. So I just intentionally did not present this numerical result. But let me show you some results. Actually, I compared my algorithm and several existing algorithms such as FedPD, FedVR, FedDuality, and so on, applied to this kind of multinomial logistic regression. And I tested all the algorithms on two different data sets, MNIST and Cypher10. And first, this figure is the comparison of all the algorithms applied to MNIST dataset. Actually, for almost of the algorithms, slope are almost the same. It means that they share almost the same linear convergence rate. But it is interesting to see that in my algorithm, dual FL, there is very fast energy decay in the first several iterations, and then goes to the linear convergence behavior. So I observed that my algorithm, the energy curve of my algorithm is consistently lower than those of the other algorithms. But I don't think that my algorithm is absolutely better than the existing algorithm because this performance highly depend on the tuning of hyperparameters and all the other aspects. But actually, I did my best to tune the hyperparameters of all the algorithms, and I observed that my algorithms shows the best behavior. And the same discussion can be applied to the result on Cypher10 dataset. This blue dotted curve, which corresponds to dual FL, this is constantly lower than all the other algorithms.
Okay, interesting. Especially the last note, the non-convex experiment, that it works so well. I mean, because all your components of the algorithm design are not are not really for non-convex problems. No, you need.
Oh,
but,
this problem is convex. I mean.
Okay. So you just use the Cipher 10 data.
Yes.
But on this convex problem. Okay. Then I understand. Okay, great. Okay.
Yeah, actually, if I expect that if I apply my algorithm without modification, my algorithm to non-convex problem without modification, then I don't expect acceleration. Maybe in order to achieve acceleration for a non-convex problem, I have to revise my algorithm significantly. But I don't have an idea. I don't have some precise idea at this moment.
Good. Okay, there's a question by Xiaowen.
Yes.
I can.
Oh, I just clicked.
Oh, okay, great. Maybe. Oh, he's unmuted. Yes, so you can ask.
Thank you for the great talk.
Thank you.
I just want to make sure what kind of communication acceleration did you get for the convex and smooth optimization?
Convex and smooth. Okay. So you mean that we do not assume the strong convexity of the problem, right?
Yes.
So this theorem corresponds to the case when the cost function is smooth but may not be strongly convex. In this case, my theorem says that this gradient error is bounded by this rate, bounded by this term, and in order to make this term less than epsilon, then the number of communications n should be less than this one, and this one is a big O of 1 over square root of epsilon. And if we apply just simply gradient descent method to make this one, if I apply gradient descent method to the federated learning problem, then this complexity is 1 over epsilon, which is lower than this 1 over square root of epsilon. In this sense, I just said that we achieve communication acceleration.
Okay, thank you very much.
Thank you.
Yeah. Okay. Are there other questions? We have a lot of time to go. That's fine. Yeah. I don't know. Maybe some last comments then.
Yes.
So I mean, you say some. Okay. You have a lot of highlighted a lot of small things that are still missing for your method from your method. Now, one is this maybe for stochastic noise in the problem.
Yes.
Of the data. So is it, let's say, do you see any hope that this can be added? No, I mean, let's say if you go back to this subspace correction methods, is there do they work also for the stochastic case?
Actually, as I know, there are no existing works on subspace correction method that deals with some kind of stochasticity. So this is why my current method does not cover the case of stochasticity. So this is my ongoing project. So as you suggest, I have to consider several stochastic settings in order to be more practical.
Good. Okay, no, but then a lot of open problems and so on. No, and I think it's really great to hear from you and have this presentation. So if there's no, okay, there is actually Grigory has a question, so you can speak.
Hello.
Hello.
Thanks for your talk. So I have several questions. So first of all, I want to make a comment on Sebastian's question about stochasticity.
Yes.
So as far as I understand, you can use any method to solve your like local problem, right?
Yes.
Because it's written in argmin notation. Yeah.
Yes.
So for this problem, we can use some stochastic method.
Yes, we can use stochastic solver for local problem.
Yes. So in some sense, you already have results for stochastic case.
Yes, in some sense. But but as I know, I have to consider some kind of communication compression. I mean, even though I obtain some good solution in each client, or when we collect the data from clients, there were some noise. There were some additive noise in the collected data. So, but my client algorithm does not cover this kind of issue.
Okay. So my question is, what do you think about obtaining results for just general convex case without additional log factor 1/epsilon?
Sorry.
I mean, in current result, so the analysis for general convex case is
Yes.
based on strongly convex case, right? Because
Yes.
you use this like regularization trick with alphas, right?
Yes.
So, and this trick leads to additional log 1/epsilon factor, right?
Yes.
So my question is it, how do you think, is it possible to prove a general convex case, result for general convex case without this regularization trick?
I'm not sure because my convergence proof heavily relies on the existing result on Vista, and Vista assumes some kind of smoothness property, and the strong convexity of the primer problem is essential to ensure the smoothness of the dual problem. So maybe in order to obtain some result without a regularizing technique, I have to fully reanalyze. I have to make some totally different approach.
Yeah, but I think this is maybe not really practical, but in terms of theory, it's quite interesting question.
Yes, I agree with your suggestion. Maybe just maybe not simply adopting the existing analysis of Vista. Maybe I can develop some new theory that can be applied to general convex region, because my current algorithm can be formally applied to general convex problem without any regularization term.
Okay. Thank you for your answers.
Thank you.
Yeah. Okay. Yeah. Thanks, Grigory, for clarifying, and this comment on the stochastic case. No, that is somehow probably already have to some extent. No, maybe not. I need to maybe really write it down and so on. It's very good. Okay. So if there are no more questions from the audience, then let's thank the speaker again.